Very exciting to see everybody in real life instead of those surrounded by Zoom boxes. And welcome to the Simons Institute. I'm very glad we could host it here. We've had a change to the schedule. So Sasha Racklin's talk this afternoon, we've had to cancel. He's on his way back to deal with a family matter. Unfortunately, we'll have a gap in the schedule there. It just means we have a bit more of a break before the reception this afternoon. A reminder to wear your masks inside, and please keep the food and coffee outside, and don't bring it into the auditorium. Okay, and some introductions. Darren is doing the videography, so he'll be setting up speakers with microphones and hooking up computers and so on. And a big thank you to Kalani Penland for all of her work in getting things together. Thanks, Kalani. Also, thank you to Nike, who I hope is able to join us by Zoom, but couldn't make it in person because of teaching. So thanks for all your work, Nike, if you're on there. All right, and I'll hand over to Misha.
Okay, so let's start the first session with Fred Koehler giving a talk on uniform convergence.
Is this working? Okay, it's working. All right, great. Great. Thanks everyone for coming at 9 a.m. on Monday. This talk is about uniform convergence. And so it's basically about some attempts to understand how generalization theory works in the benign overfitting setting. And it's a joint work with Lija, Danica, and Nati. Okay. And I thought, since it's kind of like a 9 a.m. talk, I'm going to start off maybe slow for some people. I'm going to go just remind you what's benign overfitting, what does uniform convergence mean. But I think it might be a helpful reminder and help get the notation set. Okay, so yeah, let's really start at the basics. So in this talk, we're really going to talk about learning with the supervised and with a squared loss. So you have training data, which is sampled ID from a distribution. And we're always going to label the covariate or feature vector as x1 and the label as y1. The goal is to find a predictor, which basically can predict yi from xi, and it'll be measured in terms of the error on a test sample, which is a fresh sample from the same distribution. And you look at the expected error in the squared loss. So this is the population loss functional, or the test loss. And of course, to try to get a good predictor, what you do is minimize the training error, which is just the average squared error over the data. Okay. There's just a little fun visualization. Here's a ground truth curve. So in this case, the distribution over X is like uniform from 0 to 10. We sampled like 10 training points. And then if you do empirical risk minimization with a degree 5 polynomial, you get a curve like this. And you can kind of see that this is a pretty good fit, in the test loss, because it's kind of close to the true curve on most, although not all of the possible data points. And of course, if we fit like a degree 17 polynomial, well, for one thing, there's more than one degree 17 polynomial that goes through all the data points. And secondly, we see that although it gets a training error of 0, it has a very bad test loss. So it's clearly not close to the ground truth curve. And, this is a clear illustration of this principle that models with 0 training error typically generalize poorly, which you can find in any statistical learning textbook. And then we have this whole theory of uniform convergence, which kind of explain what is going on here. So you have the test error, which is what you care about. You have the training error, which is what you minimize with ERM. But then we also need to worry about the generalization gap, which is how different those two could be. And basically, if you go through a textbook on statistical learning theory, maybe the TLDR is you should pick a small class of functions so that the second term is small, the generalization gap. And we have all these measures of how big or small a class is, like VC dimension or Rademacher complexity. And if you make that generalization gap small, then you can kind of think that minimizing the training error makes sense because it's close to the test error, which is what you actually care about. And that's kind of uniform convergence 101. And that's kind of a foundational part of, I guess, statistical learning theory. Okay, so that was perhaps something that everyone knows. But anyway, the nice thing about this is it gives a very simple understanding of what went wrong. Its example is that we simply fit too powerful a class, so the generalization gap is very big. This is why even though the training error is very small, the test error is very big. Okay, and yeah, I think even this, okay, I know a lot of people are very familiar with this, but just as a reminder, this is a plot from a paper by Misha, Velkin, and others. And what we see is that for some machine learning models, this is a fully connected neural network on MNIST. Actually, what happens is that the training error, which is the orange curve, gets very small, and then the test error is actually pretty good. So among other things, you see that it's not the story before because the training error and test error are not close. So the class is not very small. Of course, there's also this famous shape, the double descent curve, where the test error goes down and then up and then goes down. We're not going to be super concerned with that shape because we're really only going to look at the right-hand side of this plot. Okay, but so that's a definitely an interesting empirical phenomenon that you can get this behavior where getting the training error to 0, even with noisy data, can be a good way to minimize the test loss. And this is another the slide from the same talk by Misha at the Simons Institute 2 years ago. And you can kind of get this kind of behavior even if you add noise to the labels. So in classical statistical learning theory, if there is no noise in the model, then it makes sense to find a perfect interpolator. But generally speaking, you would think it's a bad idea if there's noise, and yet nevertheless, it can work in practice. Okay. And so the rest of this talk is going to be about this model, just Gaussian linear regression, which I guess is one of the most popular theoretical models to try to understand this phenomenon. That's a maybe incomplete list of all the works considering this model. Of course, there's other models like kernel learning or different classification models where people also study and observe double descent, but maybe this is the most popular one to study. And I guess it has some connections to kernel learning, obviously. And so formally, the model, we're going to sample covariates from a Gaussian distribution with arbitrary covariance. Then the response is a linear function of the covariate. So yi is w star dot xi plus noise. And we're always going to have a positive amount of noise. So we're not in the classical setting with no noise where it makes sense to interpolate. And sometimes I'll use a matrix notation. So, this is also just conventional notation for linear regression. You put the data into the rows of matrix X, and then the response is this vector Y, which is XW star plus the noise. And just like before, the ultimate goal is to minimize the test error on a first sample. Okay, and then with this notation, the interpolation is just when Y is equal to XW. So it's the training error is 0. And the phenomena of benign overfitting, it does happen in this model. And so in many cases, if you look at the minimum norm, L2 norm interpolator, you'll find that the population loss goes to sigma squared. So, or it's close to sigma squared, which is the optimal. And there are some conditions which essentially characterize when this happened, which are due to Bartlett et al. But so I'll get back to those conditions later. But for now, all we need to know is that this is a model where benign overfitting certainly can and does happen. Okay. And okay, so what happens now? We go back to the uniform convergence story, and we can try to understand what's going on. So we can try to upper bound the test error by the train error plus generalization gap. Okay, so what's the test error? It's sigma squared. So that's like when benign overfitting is happening, then the test error is sigma squared. The training error is 0. And so in order to prove the optimal bound on the test error, we need that the generalization gap should be like sigma squared, right? Okay, and just a reminder, so here I changed notation a bit, but here K is the class, so it's a collection of simple hypotheses containing W. And in particular, you would normally look at the set of low norm predictors. Okay. And then the issue with this is it actually just doesn't work. And so this is kind of considered a failure of uniform convergence. And what happens is just that you can compute the generalization gap over, for example, the class of low norm predictors. And if you pick a norm that's big enough to contain the interpolators, then the generalization gap is much larger than sigma squared. So I think more precisely, what's shown in these works is that, for example, if you look at the L2 ball and you look at it with the absolute value, you get something that's like infinitely larger than sigma squared, which is really bad. Yeah, okay, then you can think, well, we only need an upper bound, so you can remove the absolute value. Even then, you'll get something larger than sigma squared, although it's much better, but still it's too large. Okay. Yeah, and I guess also you can just plug in all of your favorite generalization bounds for linear regression, and they all have this kind of problem because they're trying to control. Even if they're not literally of this form, they generally speaking don't work. And so this is again another slide from Misha's talk. And it's just kind of summarizing the situation, which is that all of those generalization bounds, they don't really seem to work for this situation. And it's because you upper bound the test loss, right, the training loss plus a bound. But then the bound usually has some large constant factors and so on in it. So you get an upper bound, which is often trivial or not really informative at all about the test loss. And this is kind of part of, there's been lots of papers discussing related issues to this. And pointing out that when you plug in generalization bounds, they just don't work in this situation. And with varying levels of like maybe optimism and pessimism. So I think, because the generalization bounds don't seem to be working, people have kind of suggested that maybe the uniform convergence theory is a little bit obsolete, at least for understanding this kind of big models with small training error. And of course, yeah, other alternative methods have been proposed to study this. Okay, so because generalization theory doesn't seem to be working, what you can do, at least in the linear regression case, is study the closed form. I mean, you can study the empirical risk minimizer using its closed form solution, which is the pseudo inverse. And based on that, okay, it's good because you can theoretically understand what is going on. So you can prove that even though all those generalization bounds didn't work, you can recover the correct behavior, that the minimum norm interpolator is in fact consistent. And so I guess that's kind of a success, right? So you can, yeah, go ahead. Yeah, I guess I'm being a little bit vague. So in general, you can consider that there's a sequence of covariance matrices and they satisfy certain conditions. And so the sequence of covariance matrices, they're growing with the number of samples n. And the Bartlett et al. Results basically give you essentially a characterization of what properties that sequence of covariance matrices need to have such that the minimum norm interpolator is going to converge in population loss through sigma squared. So that's is a sequence of population covariances. Yeah. So that in probability will converge through sigma squared. Yeah.
So in particular, can you say something about consistency for a fixed problem, like a fixed population?
Well, like if you have because you need to change the covariance with the number of samples, because sorry, we're always in the over-parameterized regime, right? So if I grow the number of samples, I can't keep the covariance fixed because the covariance is like d by d, and d needs to be bigger than n. So you always need to have a sequence of covariance matrices.
You consider like a kernel setting or something like that.
Yeah, you could consider a kernel setting. Yeah, that's right. So people also studied kernel learning. At least in this Gaussian linear regression model, you'll need to keep changing the size of sigma. Oh, you could, yes, okay, you could have an infinite, that's true. Yeah, Andrea is right. Yeah, you can have an infinite covariance matrix, and that's also, yeah, discussed in the Bartlett et al. Paper. And you can write down the conditions for an infinite covariance matrix with the right properties. I think there is something where, like, maybe if you look at a sequence of covariance matrices, you can get more, like, you can sort of get more general conditions. But yeah, that's right. So you can also write down conditions for an infinite one, but maybe it's better to look at a sequence. Yeah. I guess you know, there are a lot of experts in the room, so please feel free to comment or raise questions. Okay, so that's great. And so why am I giving this talk if we kind of understand what's going on in this model? Well, there are things we don't understand. So you can see we don't understand what's going on with the generalization bounds, except that maybe they don't work. And arguably, I would say that there's kind of a philosophical question which hasn't been answered. And so it's philosophy because it's not really a concrete question, but arguably this analysis, although it proves that the closed form, it proves that the minimum norm interpolator works, it doesn't directly answer the question of why we picked the minimum norm interpolator. So we have lots of different interpolators, and the minimum norm interpolator, we might think it is the simplest one because it has the smallest norm. But in the analysis, norm does not really play a role. In particular, there's no direct link made between the norm of a predictor and its test error, which is what a classical generalization bound would do. And so it's that part is, yeah, not entirely made clear by the existing analysis. Yeah, what the norm has to do with the test error. Okay. And so it leaves us with this question whether the conventional generalization theory could explain benign overfitting, at least in this model. Okay, and what we're going to do is we're going to consider sort of a plan of attack, which was outlined by Zhao et al. In this 2020 paper. And what they do is they say, okay, well, uniform convergence, it could mean many things. We need to be careful about what we're saying by uniform convergence. And really what we should look at is the worst case error among interpolators. So it's the kind of a localized version of uniform convergence where you put in the constraint not only as a predictor in this set, but also that the training error is small. So you can visualize it this way. There's the predictors which have low norm, and there's a smaller set of predictors which have low norm and low training error. Okay. Yeah.
You're going to take the norm of the minimum norm. I mean, the norm of the minimum norm.
We're going to take it to be big enough that it contains the minimum norm solution. Yeah, not to be exactly the minimum norm solution, but yeah, a little bit bigger. Yeah.
But that isn't this a little bit obvious?
It's obvious that if you pick exactly the minimum norm, that it will work.
But the norm of the minimum norm will concentrate, right? So it does concentrate.
Right. So okay. Like one thing that's going to happen is like something that's maybe not obvious is that if you multiply the norm by like 1 plus epsilon, how does the test loss change? And then we're going to be able to understand that. So even if you don't literally get the minimum norm, but like you're a multiple approximation, you would still have a very good generalization guarantee. Yeah, that's a good question.
Is the minimum norm like data dependent?
Yeah, so the minimum norm is data dependent. So here we're thinking B is like, because the norm concentrates, B would be like a high probability upper bound.
You can know that without running the algorithm.
Yeah, you can know that like if you have yeah, like if you like, oh, obviously if you have all the parameters of the problem, you will know that. You can also get upper bounds on that, which don't require to know all the parameters of the problem. But and I guess at the very end, like I'll also talk about a bound which would not even need to have a priori knowledge of B. Like you could plug in the actual norm, but I guess conceptually you can almost think, you can union bound over all the B's. And since that's just a one parameter dimensional family, that shouldn't be too expensive. Yeah. And yeah, so this is uniform convergence, not exactly of the form that I started out with in the first slide, but it is a kind of uniform convergence which has been studied for a long time in learning theory. And so, for example, this is from a textbook by DeRoy, Giorfi, and Lugosi. And you can see here, what they're doing is they're analyzing the generalization error of a zero training error predictor. The thing that is a bit different from our setting is that they are assuming that there's no noise in the model. So, it will correspond. I mean, they're in a classification setting and they assume that there's no noise. So it's not the same setting, but they are using the same kind of bound, which we would call uniform convergence of interpolators. And so this is a classical notion of uniform convergence. Okay, and so anyway, here's the conjecture from Zhao et al. The conjecture is that you have a very sort of straightforward kind of generalization bound, which is the test loss is upper bounded by the norm squared times basically the expected size of the covariance squared divided by n. So that's very similar to what you see in conventional generalization bounds, except that there's no leading constant factors. And because if I double the right-hand side, if the right-hand side is sigma squared and I double it, I would get 2 sigma squared, which is very bad. So it is a very important part of this conjecture that it doesn't have a leading constant factor. And you can sort of think this would answer our philosophical question because it would show that actually there is a meaningful relation between the amount of norm you need to interpolate the data and the test error. And in particular, it's good to minimize the amount of norm because that is the upper bound on the test error. So that would sort of create a link between norm and test error, which we don't have. But when they made it, it's, yeah, go ahead.
So here, what is all small of 1?
Yeah, I'm gonna be a little more formal later. Yeah. So the conjecture, like, because they stated like a little bit, I don't know if Nadi wants to say, but like, maybe it's better to write 1 plus little of 1 times the other thing. That would be, yeah.
But this doesn't say that there's no better norm. You have another upper bound, which is better.
Yeah, that's right. So this upper bound might not always be tight. Yeah. But we're going to show that it's tight enough to explain a lot of things.
So does this B somehow depend on n because you need like higher norm to interpolate more samples?
Yeah. So the little of 1 everything, can be made into like actual error terms. So then you won't have to worry about that. Or you could consider like some kind of sequence of matrices. Yeah. But basically, the little of 1 term is actually going to be things that are much smaller than this term, which is going to be very large. Yeah.
So this is for interpolating classifiers only, or it's the same thing also if you index it?
Yeah, so this bound is only for interpolators. Yeah, so that's right. So the form of the bound, I think I'll get back to this maybe at the end of the talk about how you would state a bound like this for also for the classical regime. Yeah, but right now this conjecture is only for interpolators. So it's only on the right of the double descent. Yep.
As stated, it just holds for any b and any n.
Yeah, but you have to be able to interpolate the data.
So then, I mean, since it's only for zero error predictors.
I see. So like, I mean,
Well, this
that would be-
stays it, but it's something very similar might hold, right?
It should be relevant, right?
Yeah, otherwise it's trivial. It's trivial.
Yeah, I mean, like, as in the set.
Well, if you put that as a constraint. If you put L of W equals 0 constraint. But we do have this, right? It is a constraint. No, I understand. I'm just asking. Maybe something similar. Without.
Okay, we will see what the.
Yeah, at the end of the talk, we will see how to generalize this beyond the zero case. Yeah. And it is something similar to this. Okay, so I just wanted to say, yeah, I guess in the collaboration meeting in last year, Lija talked about this work, and what they did in that work is not only, of course, just state the conjecture, but they proved it in a certain case, which is called a junk features model. It's basically a specific model of the covariance. Yeah, I guess I won't describe exactly what it is. So they proved it in that model, but the proof doesn't apply to a general covariance. And also in a later work by Yang, Bai, and Mei, they also studied uniform convergence of interpolators, and they showed something of this flavor happens in a certain random features model. Those are the main prior works on uniform convergence of interpolators. And what we're going to do in this paper is prove the conjecture in the general setting of the Gaussian linear regression model that I described. We're going to prove this inequality, and also we're going to show not just that this inequality is true, but that it's explanatory. So you can show how to recover the benign overfitting conditions from Bartlett et al. And you can also get some new results which generalize beyond just the L2 norm, minimum L2 norm interpolator. So that's what we're going to talk about. Okay. So this is generalization bound. Yeah, I guess I wrote this with the little of 1 and little of n. In the paper, there are the like finite sample bounds in terms of quantities which are generally speaking small. So yeah, I can answer questions about exactly what the little one means, but essentially this is what the bound says. It says, I'm going to look at a class. So the way this model is set up, the class is just a subset of RD. I'm going to look at the Gaussian width of the class, which of course is a natural measure of the complexity. I'm going to talk about that a bit more on the next slide. And what you get is that the test loss of interpolators in the class K is upper bounded by the Gaussian width squared divided by n. And in this Gaussian width, there's a sigma to the 1/2. So that expresses, well, you can either think that in the definition of Gaussian width, we're actually sampling h from normal 0 sigma. That's totally equivalent. Or you can just take the set and multiply every point in the set by sigma to the 1/2, and it's the same. So either way you look at it, it's a Gaussian width squared divided by n. Okay, and this is going to recover the conjecture that I stated before. I wanted to say the Gaussian width. Okay, maybe people are more familiar with Rademacher complexity. These are very similar concepts. In fact, in our example, they're actually equal. Okay, so Rademacher complexity measures how well functions in a class can correlate with pure noise in the form of random signs. This is maybe the textbook notion that you see in a textbook on learning theory. And we can compute the so-called the expected Rademacher complexity is averaged over the data of the class of linear predictors where the predictor is in a set K. And so this is the definition of the Rademacher complexity. I average over these random signs sigma and over the covariance x. And I look at the supremum over the class of basically the dot product of the function with the random signs. So now, okay, here the class is linear functions in a set K. So I can just plug in the definition of the class. This is equivalent. I guess I use like linearity. This is just the same thing where I plugged in the definition of the class basically. And I split the 1 over n into 1 over squared n and 1 over squared n. And now what you see is like this 1 over squared n sum of the random signs times the xi's. Well, that actually can be simplified a lot, right? Because that's, if I take a Gaussian and I multiply by a random sign, it's still a Gaussian. If I take a bunch of independent Gaussians and average them appropriately, I just get a Gaussian with the same covariance distribution. So that expectation can be simplified into expectation over just one Gaussian. The Gaussian has covariance sigma, so this is the Gaussian width of sigma to the 1/2 K. And yeah, because there's a 1 over squared n factor, I guess it differs by that scaling factor, but otherwise these are exactly the same concept in the case of Gaussian linear regression. Okay. And so if you like, you can state the generalization bound this way. It says that the test loss is upper bounded by the Rademacher complexity squared of the class. So unlike conventional generalization bounds, maybe it's not for an arbitrary distribution of x, but it is of like totally the same form in the sense that it upper bounds the generalization error by a complexity measure of the class. Okay. Yeah. So it's a small O of 1. I think for this setup, yeah. So the small O of 1 includes something like a 1 over square root n term. So that like square root log So yeah, so, you know, there's a multiplicative, so it's not literally 1, but it's like 1 plus a constant times square root log 2 over delta over n. So that's in the little of 1. There are also some small additive terms. So because at some point we use Gaussian concentration over the class, there's something like the radius of the set divided by square root n. And those are the little of 1 term. And that's an additive term. And oh, okay, yeah, sorry. There's a more general way to state this. Sorry, I've been kind of skipping over this. Like, to really get the full Bartlett et al. Result, you need to integrate this notion of a covariance split, which makes the bound a little more complicated. So for most of the talk, I was planning to just kind of omit that detail. But if you put that back in, you can replace, like what I said is true, but you can actually replace this Gaussian width by a generally smaller Gaussian width where you replace sigma by this sigma 2, and then you'll get the radius of sigma 2 1/2 times k. Yeah, so there's a bunch of those things. So that's pretty much it. So basically, there's a multiplicative factor of like square root log over 1 log failure probability over n, and then there's an additive term which comes from the radius of the set, and that's basically it. Yeah.
Sorry, I guess I'm missing something. How does sigma 1 and sigma 2 come in? Because in the definition, in the statement, you only have sigma.
Yeah, that's right. So, okay, maybe I can write with this marker. So more generally, like the more general bound looks like so you would get something like square root rank 1 log 2 over delta divided by n times the Gaussian width of the class squared divided by n plus something like I forget exactly what it is, but it's something like it's possible that's squared or something, but that's basically like for people who like to see the precise generalization bound, it's something like this, and there should also be like a confidence term here. Okay, so this is multiplied by this. So this is one part of the finite sample bound. So, and here I'm assuming sigma is split as sigma 1 and sigma 2, 0, 0. So you can make the bound a little more accurate by, basically adding this kind of split feature into it. And then in this split, in this term, you have the rank of sigma 1, so you don't want to make sigma 1 too big. So that's really more of the full gnarly details of the bound. Oh, sorry, this is L of W, and this is the inequality. Okay.
And but for this one, for the statement you don't need any split.
Yeah, this is true without doing all the splits. The split just makes it tighter. That's
Does it follow the split bound from this one, or you have to follow?
Yeah. So I'm going to explain in these slides. I have like a proof sketch of this bound, and you have to do a bunch more work to get the split bound. Yeah. So the split has to do with like, this is kind of like a non-localized bound in some sense, and the split lets you do some kind of localization. So they're related, but the split is more complicated.
If you have a true coordinate, forget about the interpolation or anything, right? If you can get about the norm. But suppose you have a situation where you have a small number of dimensions that are large, and then the rest which are making up. And so you can control a few number of dimensions using dimensionality, irrespective of their scale, and the rest using the scale. So this is the split.
Yeah, so the split, it's like this effective dimension notion, right? So if, like in, I guess in kernel learning, there's like some work by Tong Jing and others, where it's like if you want to get an optimized bound for kernel regression, like looking at basically the norm of the data is not quite the optimal thing. You should take into account the eigenvalue structure of the kernel matrix, and basically you can like a few large eigenvalues of the kernel matrix don't cost you that much in generalization. So that it's actually like a classical thing that shows up in benign overfitting too. Yeah.
Yeah, something that.
Yeah, go ahead.
Peter work, there is this notion of
Yeah.
now less not that you don't have.
Right. So that's going to show up too, because we still need to calculate the norm of the minimum norm interpolator, and that's like this. Maybe he has 3 conditions, and like that's the 3rd condition that will show up there. Yeah. But the generalization bound is just always true. It's just sometimes the norm is big. Yeah. Okay. And so, like I said, this will recover the conjecture, because you can just compute the Gaussian width of the L2 ball. And since this is also the Rademacher complexity, so if you think about it, you might be familiar with this calculation already from looking at Rademacher complexity. Okay, so we recovered that conjecture, and I'm going to talk a bit now and a bit more later about why this explains consistency of benign overfitting. And last, like we were saying, this has some benefit because it tells you not just that the minimum norm interpolator will generalize well, but as long as you can kind of get a low norm interpolator, it has a good generalization guarantee as well. Yep.
There's something like to use this, there's some dependency on sigma that must come in to the B.
So B, you're gonna like this bound is always true, but if you pick B that's too small, there's no interpolators, so it's not a very interesting bound.
So like to show consistency, you would want to show that that the loss converges to the.
Yeah, exactly. And so we'll need to upper bound B, and I'll talk about that. So, okay, these are the benign overfitting conditions, which we've been talking about. And yeah, the first 2 are basically standard in kernel learning, I think. And the third one is very important for benign overfitting. I'm not going to go into too much in what it means, but it lets you fit the noise without very efficiently. Okay, and later, if we have time, I'll go into the proof of this using our technology, which would make clear why those conditions would naturally show up. But anyway, what we show under these conditions, the benign overfitting conditions, you can prove a upper bound on the norm of the minimum norm interpolator. And okay, it might look a little weird, but it's exactly the thing that's going to cancel out the other terms in the generalization bound when you plug it in. So, and so that's I guess among other things telling you that this bound is actually useful. Like, so it's tight enough to explain benign overfitting. And of course, I didn't tell you how we prove the norm bound, but I'll get to that later. Okay. And I thought I would just include like a fun plot. So this, you can also just, if you didn't want to analytically compute the norm, you could try to just empirically compute in a bunch of examples. So this is just some example where benign overfitting happens. You have a covariance with one large eigenvalue and many small eigenvalues. The blue curve is the test loss, and the orange curve is what you get just by plugging into the generalization bound. And so these are benign overfitting situations. You can kind of see as I'm increasing the dimension, so the number of very small features, the test loss is getting close to the Bayes error, or like sigma squared, the minimal error. And you can see that this bound is capturing that. So this is kind of a visualization of what I was saying in the previous slide, that the bound is tight enough to understand consistency of benign overfitting. Okay. The band is because the norm has a bunch of variance. Yeah, so asymptotically, if you are in the like n to infinity limit, that variance doesn't matter. But yeah, and that's why we have all these confidence terms in the bound, because the norm does vary, and I'm plugging in the bound with the norm of the actual data. I guess if I use the high probability bound on the norm, it wouldn't have so much variance, and it would just be bigger. but it will look essentially the same. Yeah, so it is that's what the band means. It's a standard deviation. Okay. Yeah, let me briefly say, I'm not going to go into the details about this. Because we have a Gaussian width bound, you can plug in for other geometries. And one of our favorite norms besides L2 norm is L1 norm, which we use like in lasso and eta boost compressed sensing. And people were asking what goes on with the L1 norm ball and analyzing this. And what you can show is that in the junk features model, which kind of looks like this, it's a covariance with, like I said, identity and many very small eigenvalues. You can use our technology to prove that the minimum L1 norm interpolator is consistent with this kind of covariance structure. And we also, generalize the benign overfitting conditions. So, we have some general conditions for a general norm, and just specializing it in this example shows that the minimum L1 norm interpolator is consistent in this setting. And I think this is, to my knowledge, it was the first time that it's proved L1 norm, minimum L1 norm interpolation is consistent. It's not so easy to analyze directly because the basis pursuit solution doesn't really have a nice closed form like the ridge solution does. Okay. Yep.
Do you have some sort of so it works for L2 and L1 does well?
Okay, like it works for L1. I should mention that you need a very large number of features for this to work, and I think there are some follow-up results showing that it's kind of tight. So like you need like so many features, at least in this specific model, for it to work, that it's hard to get it to show up in a simulation. So the L2 norm is a lot better, I think, in that sense for benign overfitting. Sorry, yeah, I'm not sure that answered your question.
I'm curious. I mean, what about L3 or something?
L3.
Is it for any norm or is it?
Yeah, our CRM works for any norm, but we only tried it with L1. Yeah, I think with this kind of junk feature model, it's a good question, which I haven't thought about. I think it should work also for other norms, as long as you take a lot of features, but I'm not 100% sure. Yeah.
Can you say something about the rate of convergence to the consistency?
Oh yeah, so like I was saying, yeah, the rate of convergence is example extremely slow. It's like you need for n samples, you need like a number of features, at least based on our analysis, which is exponential in the number of samples. So that was okay. And in this paper by Ju et al., they have some kind of lower bound saying that the rate of convergence has to be extremely slow. So
For both L1 and L2, do you know which one is slow, but which one is slower?
yeah, L2 is pretty fast. All these bounds, like the convergence is like 1/4 root of n or 1/4 root of n, but for L1 is like 1/square root log n. So that's
I see.
yeah. There's no convergence rate issue for the L2 norm. Okay. So I thought, yeah, I'll try to explain the proof idea. I think actually one benefit of this analysis is that, well, I don't know, like it's not extremely simple, but I think it's not extremely complicated either, and hopefully I can convince you of this. So I think it kind of shows uniform convergence can be helpful even if you just want to get the answer. Okay, so anyway, the key thing is we're going to view the generalization gap as a random optimization problem. So what does it mean, generalization gap? We're going to look at this class of interpolators in the set K, and we're just going to find the thing that has the worst test loss. So that's the optimization. With Lagrange multipliers, I can write it as a max-min optimization. And then, as I imagine many people are familiar with, there are really good tools for analyzing random optimization with Gaussian data. In particular, there's this result called Gordon's theorem, which has like a huge number of applications in like compressed sensing and high-dimensional statistics. So anyway, basically, Gordon's theorem says if I have a max-min problem like this, then it involves a random matrix, but it can be upper bounded with high probability by an optimization which just has random vectors. Right? So Gaussian random vector G and H. Okay, so, and Gordon's theorem is exactly just like a recipe that tells you how to convert the random matrix problem to the random vector problem. So you get this. So there's like basically what happened is originally there's this interaction between the lambda and w star minus w and this random matrix X. But now you get these two terms where it's a laser pointer. Don't worry about that. You get these two terms where the interaction between the Lagrange multiplier lambda and the predictor w becomes much simpler. So the lambda is now just a dot producted with a random Gaussian vector, and the interaction with w is just contained within this norm term. And then you have an additional term which is similar, which is like symmetrical. And so the short of it is that that theorem automatically converts the first problem to the second problem. Now you can sort of explicitly solve for what's going on in that problem. So I just wrote the problem again to make a nice substitution. So you get this optimization problem. Okay, and now like the great thing is there's a min over lambda, but you can kind of think, you can kind of just solve this explicitly, because either the min player can pick a really big lambda and take this loss to negative infinity, which is the case basically if the first term with lambda is bigger than the second term with lambda, or they can't do that, and the best thing they can do is pick lambda as 0. And so just formalizing that, you get basically just applying Lagrange multipliers the opposite way. You get that it's a maximization over all the vectors in this set, which satisfy some inequality. So, and then that inequality is just saying the first term is upper bounded by the second term. And then, okay, so this has a norm of a G times U plus the noise C, but G and C are both Gaussian random vectors, and they're independent. So they're very, in high dimensions, you know, those are almost exactly orthogonal. So you can just say use like Pythagorean theorem to simplify that constraint, and you'll get this U squared plus sigma squared is at most H dot U squared over N. Okay, and then it seems kind of magical because now you are trying to maximize, and the constraint is exactly telling you an upper bound on the optimum. So you get this inequality that this thing you care about is upper bounded by the maximum of this dot product squared, and that is essentially the definition of the Gaussian noise squared. So that's basically the proof sketch of the main theorem. Yeah, when you make it formal, there's a bunch of technical details. The covariance splitting is actually a little bit important to get all the concentration inequalities to work out. But that's essentially the calculation. Okay. And yeah, you have to do a more complicated argument for the covariance splitting, but you know, it's not wildly different. Okay, so I thought I'll briefly show this norm bound thing. So these are, you know, just to avoid having to talk about this covariance split all the time, this would be like a simpler benign overfitting conditions, which are not as general, but don't have a covariance split. So basically the norm of the data cannot be too big, and you still have this condition that there's some kind of large effective dimension condition, which is key to enabling benign overfitting. And you want to show some kind of upper bound on the norm of the minimum norm interpolator, and you want to show something like this. Okay, I wrote it a bit differently. So there's a W star on the right hand side. That's actually that's small compared to the last term, so it's the same as what I wrote before. But anyway, if you have that, then you can plug it in to the generalization bound, and like I was saying before, you get the sigma squared plus lower order terms. And you can already see, if I phrase it this way, why we have the first condition is that the norm of W hat squared in particular has the norm of W star squared in it. And the first condition is just telling you that if I plug in W star squared, that the term on the right hand side is little o 1. So that already makes clear why we have the first condition, which is kind of the standard condition. Then to understand where the second condition comes from, you can just do a similar kind of analysis where you compute the minimum norm. The nice thing is that because of the way our framework works, you just need to upper bound the minimum norm, which actually makes, I think, the calculation a lot easier than if you needed to compute it. Well, it makes, you can use inequalities then, right? So that's very convenient. So yeah, first of all, you can use triangle inequality to get rid of the W star term. So you just need to find the minimum norm interpolator in a setting where there's no signal. Then using Gaussian comparison like before, you reduce to some optimization with a constraint. So this is totally analogous to before. Now to solve this optimization, it's not actually clear how to solve it from here, but you can just kind of make a guess for what the minimum might look like. So there's a dot product. So maybe the optimum will be along the direction of the vector similar to the 1/2 h. Seems like a reasonable guess. Then you plug it in and just kind of, you can automatically solve it. The constraint now gives you it tells you how small you can take basically the norm of this interpolator W. And so just kind of automatically doing it out, you get, oh, sorry about that. You get to this, okay. And now sort of magically the second benign overfitting condition comes in, because this expression is actually very close to what we want, but there's this minus sigma h squared in the denominator. And then when you interpret everything in terms of traces of the covariance, the benign overfitting condition exactly means that you can ignore this complicated minus sigma h squared term. And yeah, again, interpreting everything in terms of traces of sigma. So the norm squared is the trace of sigma. The norm of sigma h squared is like the trace of sigma squared. You exactly get the thing we need, which is sigma squared and divided by the expected norm. So now I'm going to be quickly over that, but it's just the application of convex Gaussian min-max theorem, and all of the conditions appear kind of transparently in this proof. And actually, the proof for the minimum norm interpolator is actually, this is essentially the same proof with the covariance splitting. The covariance splitting only really complicates the proof of the generalization bound. Okay. Okay, so I have a few slides after this quickly, but basically, what did we show? Well, we showed that uniform convergence could explain benign overfitting, which brings up the question is, why did we care? Okay, and so this, I guess, is the main justification that I was suggesting at the beginning, is showing that maybe 40 years of statistical learning theory could still be relevant to modern practice in ML, and it is not necessarily the case that it's obsolete, the uniform convergence theory. We kind of saw that, like, okay, in situations where direct analysis is difficult, like the L1 norm interpolation, uniform convergence let us get the answer as to what's going on there. And finally, we saw that, in some sense, we got a more modular explanation of why the generalization happened. We saw that this third benign overfitting condition, it shows up exactly in when we ask for the predictor to have a low norm. And also we know that just not knowing anything, like that if the norm of the interpolator is small, then it should generalize well, which we didn't know before. And finally, since this is, I guess, deep learning theory, all those things might make this approach a little bit more scalable. Like, since we're not relying on the exact form solution, if we could first understand the implicit bias of optimization algorithms for deep networks, and second, prove a similar spirit uniform convergence bound, maybe we could understand why they generalize. And of course, it could be applied to other models, not just deep networks. Okay, so in a few minutes, I think I have a few minutes left, right? 5 minutes. I just wanted to say, since it came up before, like, how does a theory extend to the case where it's not just like the very over-parameterized setting, but also can capture it as a conventional setting where maybe you have less parameters than samples, and there's no interpolators. Yeah, and so of course the conventional generalization bounds would apply in that case, but they don't really work. They're too loose. And the uniform convergence interpolators only seems to work when the training error is exactly 0. So what do we do? Well, one thing we could do is we could open this textbook by Vapnik from 1982, and we can kind of see, okay, just like there was uniform convergence of interpolators in this textbook, there is also some kind of generalization which has to do with the case where the training error is not zero. And so this theorem is in like a totally different notation, and it's in a classification setting. But what it says is that the test error is upper bounded by the train error, and this is the generalization gap. And the thing is, the very important thing in this text, in the context of in the context of the original theorem, is that when the training error is zero, the generalization gap is much smaller than when the training error is big. And another way to say the generalization gap shrinks with the training error. And for them, that was really important because now they have one generalization bound which covers both noisy and noiseless setting. And so this kind of bound is sometimes referred to as the optimistic rate. And this terminology is due to Dmitry Panchenko, who had a bunch of interesting works related to this phenomenon. Okay, then how should we do it in our setting? It's like a squared loss, it's a regression, so the bound looks a bit different. But this is the main result from this paper by Srebro, Suran, and Tuari. And basically, what it's saying is that, again, it's a generalization bound, whereas a generalization guarantee shrinks as the training loss goes to zero. And in particular, if you plug into their bound with training loss zero, it looks almost like the same thing we got. It's like the Rademacher squared, except that it has like a huge constant factor of like 10 to the 5. It also has log factors. But this theorem alone does not recover any of our results, but it does seem to be a kind of the right form. Now, another way to look at it is, well, maybe we could actually make the idea of decomposing the loss work. So maybe what we need to do is we need to upper bound the test loss by the training loss plus the generalization gap. But for some reason, maybe we should take a square root first, because there's no obvious reason why we didn't take a square root, I guess. So let's take a square root. And yeah, one weird trick. And what you can show is basically that if you had done it this way, the generalization gap actually does work out. So the difference between the square root test loss and square root training loss is upper bound by the Gaussian width or the Rademacher complexity. So that's basically what we do. And this recovers uniform convergence of interpolators when the training loss is zero. Yeah, so it's very slightly different from that in the sense that there's a 1 plus little of 1 term. So like if I was doing it this, like if I was doing it this way, I should be careful to introduce some 1 plus little of 1 factors into this decomposition. But essentially it's this. And more formally, we get a bound that looks like this. So a few different ways to write it. So in the notation, more like the Srebro, Suran, Tuari paper, it's like the same kind of bound, but now we figured out all the sharp constants. Okay, again, this is only for Gaussian. Their bound is for general data. But for Gaussian, we figured out all the sharp constants in their bound. And again, okay, also, why did we take a square root? You can kind of think it's a natural thing because, lots of cases, if you have a square, you should also take a square root. So really, this bound is saying that when you take samples, distances in the empirical L2 metric, they're kind of lower bounded by distances in the population L2 metric with this additive term, which is the Gaussian width. And yeah, we actually show something stronger than this in the paper, but that's basically telling you how does this theory generalize to non-zero training loss. Anyway, just another similar plot to before. Now I'm keeping the number of features fixed and number of samples fixed, and I'm varying the regularization. So the training error is going from 0 to not 0. And this is some benign overfitting situation, which is why the population loss is getting close to the Bayes error, which is the purple line. But anyway, the bound is kind of correctly understanding what's going on here. So it more or less tracks the training loss. And even though the green curve, which is the training error, is varying a lot, this bound can work in the entire regime. Yeah, in the paper we have other plots, so you can get both sides of the double descent curve with this kind of generalization bound. Okay, and so that's yeah, like I said, we have a bunch of other things in this paper. And yeah, so there's the same summary as before. We were able to make uniform convergence work in Gaussian linear regression models. Of course, there's a bunch of interesting questions, like how to, for example, make it work for a model, that's not Gaussian linear regression, like a deep network. And one question along that line is, how can you make the theory work for non-Gaussian data? And even what is the correct generalization to non-Gaussian data? So that's all I wanted to say. So thanks.
Maybe Ben can set up, and thank you for the talk, and we can ask questions while
Yeah, I didn't quite understand what you were saying. Like, how do we not have a uniform convergence bound without the square root, so we somehow can get a uniform convergence bound with it?
Okay, so there's two things. One is that, yeah, maybe I went over this at the beginning. I didn't put the absolute value in. So if you have the absolute value in there, it totally doesn't work. And even with the square roots, it totally doesn't work. Second thing is that without the square roots, it's off, but it's only off by some constant factor. So the square roots are kind of, yeah, fixing that constant factor.
Right, so that's the value.
Yeah. Yeah.
Why is there bound concerning the population and the empirical forms not covered by like the small?
Because you would get huge constants. That's it.
maybe just what's the square root? I guess depends what you make it for. Right. So saying that if you have two numbers, x and y, and saying the difference in x and y is uniform, saying the difference in the square root of x and the square root of y is uniform, is different because it varies with the scale of x and y.
Yeah, right? Yeah, it doesn't make sense if you're considering bounds that don't involve x and y.
But this is the whole key here, right? Because x and y here are the losses, right? So saying that the differences between, now it's a training error and test error, saying the differences between training error and test error are uniform, or saying the differences of the square root, is different in terms of the scale of the error, right? So saying that the differences of the square root are uniform, right? That the differences without the square root scale with the scale of the errors. It's exactly what's going on in optimistic rate, or why for interpolators you get tighter uniform convergence. Think of it as non-uniform convergence. It's convergence that scales with the scale of the error, which is correct statement.
Okay, yeah, I think that makes sense.
But there's a way to handle that, which is by changing the covariance. Like if you don't care about the rate of convergence. Yeah.
I guess you.
Yeah. Right. That's the radius.
Yeah. All right. Let's start the next stop in U.